Okay, this is part two of going through this manuscript. It's got quite a bit of information to go through. So I was mostly in part one going through some of the background parameters that we should be familiar with. Something else that is important to recognize is this whole section in the introduction is built on the idea that impact or high force situations are related to overuse injuries during running. Something we can't lose sight of is that some impact is good. We know if we put astronauts up in space where there's a microgravity situation and they do not have a lot of impact, uh, locomotion with a lot of impact, even if they run on a treadmill up there with bungee cords, they can't simulate enough impact to stimulate positive bone growth. And so we have to find this balance in the real world with how much impact is good and how much impact is not good and can lead to injury. I've highlighted this term here, mechanical fatigue test. That's a very mechanical test that we would do with materials. And it takes me back to my undergraduate days where we did a lot of mechanical fatigue testing of different samples of material, like an aluminum piece of material or steel. And what you do is you put that material through some fatiguing protocol or some repetition. And the fatigue protocol ends when the sample breaks. And you can put under tensile load, you can put a compression load, you can put a torsional load, all these different things. And you wait and you do lots of measurements up until the material fatigues and fails. Well, we don't do that in the human body, but that concept is related to explaining overuse injuries, in that we are seeing a fatigue of the material and the breakdown of the material. Fatigue is a real funny term in exercise science, and sometimes it's very hard to define what we mean by fatigue. But we do need to be careful when we are using it to define it. In this case, this manuscript is referring to mechanical fatigue tests, which would be material failure type of, and that's how these authors are referring to injuries, is that there's some failure of the tissue level resulting in an injury. Fatigue may just be what we experience during the course of a race where we get tired. And if you look up fatigue in the dictionary, it will just say general tiredness. So it's a funny term to actually work with. But in this case, it did add some other adjectives here on fatigue, and it's referring more to a mechanical test. All right, so I did that. I talked about knee eccentric joint work in part one. And this is an interesting area. I'm not going to spend a lot of time on that in this section here, where we actually try to model the ground reaction force as the acceleration of the lower extremity overlaid by the acceleration of the entire body. And we can see some of the waveforms of the ground reaction force profile show up when we do that. Well, I underlined this term here because we've seen this term in some other papers I've reviewed, this duty factor. And again, that duty factor represents, it's again another term that we borrow from the mechanical world, where it represents how much something is turned on, how motor is turned on, how active it is. And duty factor in running is related to how active the muscles are, in essence, while the foot is in contact with the ground. And so what you do is you take a ratio of contact time to total time of the stride to represent how active the muscles would be to resist and help propel the person forward to the next step. And that obviously would happen during stance. Now, the muscles are active during swing phase. And so this is where this duty factor doesn't always show up in terms of understanding the details of gait. But in essence, it does do a neat job of trying to present in a simple form how active the body is during the gait cycle. And again, they're just talking, I guess maybe this is where I probably should have talked about positive aspect. of loading. You know, the whole idea of being able to do this type of event, whether it be a single marathon or ultra marathon or a series of marathons, is you've got to be able to tolerate the repetitive loading so you don't run into material failure. Okay, so let's get to the purpose of the study. This doesn't really lay out the purpose too well. It's a little nebulous, but in essence, it's a little bit different type of paper than what we would normally see, where we're comparing two groups or two responses to two different conditions or something like that. In this case, we've got a single subject that they're really interested in understanding, and they're going to try to understand his response over a period of time, as well as his response in comparison to other like built or like runners. Okay, so here's the purpose of the study. Usually it's in the last paragraph of the introduction. The study represents a unique attempt to examine the running biomechanics of an extraordinary marathoner and the adaptive response of the human body over time. We monitored the marathon man when he was scheduled to do 100 consecutive runs, ground reaction force, touchdown kinematics, net joint moments, muscle power, which I call these joint powers, okay, not muscle powers. So same thing as joint power here. And in the ankle and knee joints were compared between the marathoner pre-100 100s and compared to a group of uninjured distant runners matched by foot strike pattern. So they're going to take a group of runners with the same type of foot strike. In this case, they're going to be heel strikers. Okay, I think that's all I want to say there. Yeah, and tell you the truth, I was actually really excited about this paper at first because I thought they were going to be measuring some biomechanics on every one of the runs, which would have been really, really cool. But they didn't do that. They just did a pre-challenge, and then they did another one prior to and near the completion of the 100. So here's their schematic of their data collection. So the design just refers to the type of statistics that they're going to ultimately do. Here's the one subject, the runner, tested prior to and near completion of the marathon a day challenge. I'm going to actually look up these authors because I do wonder if they have some other data for other runs, and I would really be interested in what's happening over the course of those 100 days on those 26 miles. And they did do a running gait analysis at 3.3 meters per second. They don't actually give his marathon times in here. I suspect that that's going to be related to his race pace. They did do a bone density scan. I'm not going to get too much into the bone density scan, but that gets to this idea that one, some impact is good, but too much impact is going to be bad. And you start to see a degradation of the bone. It does not have time to remodel. And so you can actually see some damage to the bone. And a stress fracture ultimately is a broken bone, and the bone density is starting to get towards what's happening at the bone level. They're just going to do a paired t-test between these two different days. Then they had a group of heel strikers, and they did some other measurements of these runners, again at 3.3 meters per second. And then they did some special statistics Bayesian test. This is just having to deal with probability of hypotheses happening or being true or not, based upon this type of unequal design of one subject over here and lots of subjects over here. And then they did some additional regression analysis and looking at similar runners. All right, so let's look a little bit more. A couple things to note. One, the runner did change shoes throughout the 100 days, which makes a lot of sense. They're going to break down. I mean, he's doing over 2,600 miles over these 100 days. Shoes typically, we say, last anywhere from 300 to 500 miles. So he's going to be changing out shoes. I would really like to know more about the strategy of changing the shoes out, because I suspect that he wouldn't just go from a used pair to a brand new pair. I almost wonder if he would be rotating shoes in slowly in order to keep them all similar to each other, as opposed to big drastic changes in a worn pair versus a brand new pair. But I'd be really, boy, I would like to have a little bit more information on that. And then they talked about the running gait analysis, little details in there, which are really interesting. And what they ultimately are measuring is the ground reaction force, and they're bringing the runner into the lab. So it's not, they're not doing this out running in the track, which, or out in the path that he was using, which is outside. Which again, what I was really hoping is that they would have his 100-mile run in such a way that he would run over the force platforms during specific parts of that 26.2 miles. But that's not what they did. So that's still a good for a future study. Tibiocelerometer or acceleration. This is taking a small accelerometer, which is no bigger than this pen cap. In fact, the pen cap's much bigger. It's probably about half that size. It's typically what they are. And you put that on the distal aspect of the tibia and measure the acceleration of the lower extremity during gait. And that can be a real useful parameter in understanding some gait characteristics. It's also limited, and we'll talk about that a little bit more. Okay, and then they did some labeled marker data. In essence, this is kinematics, and this is kinetics. And sometimes we refer to acceleration as kinematics, and sometimes we refer to them as kinetics because F equals ma. But the kinematics is recording of position data and then deriving, calculating velocities and accelerations as well as angles, whereas the accelerometer is measuring acceleration directly. So sometimes people, they do make the mistake of saying that acceleration is related to force. But if you watch some other videos I do on acceleration and accelerometers in particular, you know that that's not always the case. Right. Okay, let's see. Let me switch views here, because one of the beauties of this manuscript being online is that there is some supplementary data that they have. Okay, let me change my view here. Oh, maybe I can do it from here. Screen one. I'll do this. I think that's going to be enough. All right. So if you go to the end of the manuscript, there, or somewhere, I'll find it. Maybe it's in the beginning. There's a link for supplementary data. And this journal actually has quite a few extra data sets or data pieces that they included with this manuscript, which is really actually pretty neat. This isn't the case with all journals, but some journals do this, especially when they're an online journal. So they've got some data sets here. You can actually download this and look at the vertical ground reaction force data in Excel. For a representative vertical. So this is one trial of the runner as well as the control group. And this is just some data sheet metrics for subject one. I thought I'd play this one. This is the animated kinematics. Let's hope that runs this time. And so this is just 3D kinematics, and we can do this in our lab. We put all these little markers on the runner, and then you can measure their kinematics. So in this case, they have the person set up as a skeleton, but these are all different markers that are placed on the person. And now we can get knee angle, we can get ankle angle, and we can get these in 3 dimensions just from the side view. So we can look at knee flexion extension, or we can look at knee internal, external rotation, or we can look at leg AB and abduction. So looking at angular kinematics in 3 dimensions as well. And same thing with the hip and the ankle. So this ends up being pretty powerful. type of kinematic analysis, you notice that they did not include the upper body. That would have been really interesting to include that as well, but that does introduce some complexities with the analysis as well. But that's I do wonder if they have another data set of the upper body, and they do have the center mass illustrated there in that teal ball. Right? And you can get the center mass from your kinematics. Right? And again, it's not a fixed point, but it's moving as the segments are moving. Okay, so that's the force platform right here. They had a 2-meter long force platform, which is actually pretty nice because it does allow the person easy freedom to hit that force platform without making adjustments. And you see, in this case, he gets both the left and the right foot to contact that force platform. But you can see the toes are hanging off the force platform here. That would be an indication that these data can't actually be used for a full kinetic analysis of running. They would just be looking at, in this case, the left foot right here. Okay, well, that foot's in contact with the ground. Okay, all right, so that's sort of neat that there is that supplementary data, and you can play around and look at those extra files. And it's good to look at, when they do offer that. Sometimes it's good to look at it. Where did I see that? It's at the end of the paper. Yeah, so just at the end of the paper, they include this note here. You can look at supplementary materials, and they give the link there. I just typed it in and thought that was pretty cool. Okay, let's keep going here. They've got their equation for duty factor here. It's funny that they put in the 2 here in the denominator. A lot of times you don't do that. You include contact time over contact time plus flight time. They're accounting for that they're doing steps versus stride here, though. All right, so now let's start looking at some of the data. All right, so now we got to dive into this a little bit. We go through some of these figures. I'm not going to go through all of them. All right, so make sure you have your figure in front of you too, because I know it's a little small here. But we've got all these data here. In blue for all their figures, that's the marathon runner. The black is the control group. And the gray, the light gray areas represent the variability of the control group, okay? So each control group member ran a little bit differently, and so you see that represented as that light gray area. But here, the blue line is the marathon runner. So they've got the stick figure that represents what the lower extremity looks like at the moment of contact for both the blue, the marathon runner, and the control group. This is obviously on average. And ground reaction force in multiples of body weight, which is very typical to use in time on the x-axis. So here, the first thing we can see is stance time is longer, and that's something that the authors really sort of focus in on. Stance time is longer for the marathoner runner versus the group. Right, so he's got a longer stance time. He also has lower forces overall. And just looking at this, okay, we'll go through the details of the paper in a little bit. But the peak here, this first peak seems lower. It seems to happen later in time as well. And this peak here is lower, and it seems to happen later in time as well. In the anterior-posterior ground reaction force, the horizontal, remember there's 2 horizontal directions, medial-lateral and anterior-posterior. This is the anterior-posterior. This is contact, this is takeoff, this is multiples of body weight on the y-axis in force. He has less braking, less propulsion as well, less slowing down in the control group, and therefore less of a need to speed up to run this. Remember, this is all running at 3.3 meters per second. All right. Constant velocity, we say, but in reality, velocity is slowing down below that and then speeding back up so that the person is overall running 3.3 meters per second throughout this entire stride. Okay, this part here is actually just zoomed in of this part. Okay, so let me go through these plots over here. So now we've got the ankle joint and the knee joint. I'll go through the knee joint more so than the ankle joint. The reference frame that they picked is a little awkward, but they picked the reference frame, and if you go back and listen to the videos I've done before on reference frame, especially for power, they picked a reference frame so that negative power represents eccentric contraction of a muscle group, and the positive power represents the power generation or concentric contraction of a muscle group. All right. So either extensors or flexors in this case, because we're doing knee joint flexion and extension. So sometimes we have to do these mental gymnastics with the reference frames in doing this, but it all works out in the end. This is landing, striking the ground at time 0. We're going through flexion and then extension. So you can see the numbers seem a little funny here, but they are using, in essence, 0 degrees represents anatomical position. In this case, they're representing a greater negative angle to be flexion, and then the flexion is decreasing. This would give us negative velocities for flexion, which is right here, angular velocity, negative velocities, okay? And ultimately, what that would yield then is a positive moment for extension. And they did this, this is an awkward reference frame in order to get your power to here. If they did the traditional anatomical position is 0 and knee flexion angles are increasing, they actually would have ended up with a negative extensor moment and still ended up with the same power. But it's awkward often to describe extensor moment being negative. And so a lot of times we like to flip these around and say extensor moments are positive, because this is what you're putting your foot in the ground. You're trying to resist going through extension. This could be resist going through flexion during the first part of stance phase. So it just seems odd that this would mathematically be a negative number. So anyways, we do a little bit of mental gymnastics. This is their knee. So we go through flexion, we go through extension, less flexion for the marathon runner versus the control group, okay? What does that mean? Going back to knee stiffness, less knee flexion would actually yield a greater or expected greater stiffness of the lower extremity. Okay, here's the joint moment. Okay, normalized to body mass. Don't worry about that. That's just dividing by the mass of the runner or all the runners, and just a way to equate them on a relative scale. And the negative moment would mean the muscles about the knee are trying to flex the knee. A positive moment indicates that the muscles that are active to try to extend the knee. Okay, so this is an extensor moment. Is how I would refer to that. In this case, the extensors are the quadriceps. The quadriceps are active throughout the entire stance, well, most of the stance phase for sure. All right. Maybe a little bit of flexor moment there, which would happen here at the end of swing as well, which we can see is actually you start to end swing phase and you start firing the hamstrings more to stop the hip from flexing, which also causes knee flexion. So you end up seeing a knee flexor moment near contact often. So that's not uncommon. Remember, we have an extensor moment. The quadriceps are trying to fire to prevent knee flexion or to stop the knee flexion and then to cause knee extension. So this side is flexion, and we have extension. So the quadriceps are firing to stop the knee flexion and then to cause the knee extension through the last portion of stance. And this is 100% of stance, okay? Go down here, percent stance. So swing phase would be next, okay? Or we would have a flight phase. All right, so that's what the moment is doing. And the angular velocity already matches what I talked about with the knee position. This is all flexion. So negative velocities are flexion and positive velocities are extensions, okay? Speeding up through flexion, slowing down through flexion, speeding up through extension, slowing down through extension, things like that. But this zero corresponds right through here, okay? Same thing. There's a funny flat region right here, which is a leveling off of the angle position along here. All right, but now we get down here to the power curve, okay? Eccentric, concentric. So negative is eccentric. No, anything below zero is eccentric. Anything above zero is a concentric contraction. And I say that because this is, these are, okay, now let's say these are the quadriceps that are acting eccentrically. And over here, the quadriceps are acting concentrically. So eccentric, concentric. How do I know that? It's because this region is all flexor moment. Oh, sorry, extensor. Sorry. This is all extensor moment. Those terms we're referring to up here. Well, actually, this phase is all flexion and extension. Okay, so it's a phase. But this is all an extensor moment. What causes extension of the knee? The quadriceps. So down here, from about here on for sure, up to about here, I'm just looking like here, this is all extensor moment. So the quadriceps are causing knee extension. And the power is negative, meaning that the extensor moment and the velocities are in different directions, right? Negative and positive, leading to a negative power. That negative power indicates that the quadriceps are trying to cause knee extension, but the knee is going through flexion, okay? It's going through flexion. So the muscles are acting eccentrically, and you can even see a peak power here. And then over here, we have the quadriceps again extending because we're in extensor moment here. We're trying to go through extension, and now we are going through extension. This is the extension phase. The angel's going up in this direction. Now I've got the extension velocity and the extensor moment acting in the same direction. So I have concentric contraction of the quadriceps. The quadriceps are trying to extend the knee, and the knee is going through extension. Not too much difference between the blue and the black here. You can start to see the blue and the black lines differentiate from each other, especially at that peak power. So what this is starting to lead to is an understanding that the marathon runner is having less peak power during eccentric contraction. That might actually be really good. You're not doing as much eccentric work, which would be the area under that curve. You're not doing as much eccentric contraction of the quadriceps. And we always talk about eccentric contractions being more damaging than concentric contraction. So maybe that's a good thing for the marathon runner to ultimately minimize the risk of injury, which is what the authors are really interested in. All right, now we'll go through a little bit of the results. I'm not going to cover the whole thing, but I'm just going to focus in on those key force verticals. The marathoner did statistically have a lower peak vertical loading rate. Right, that's, talk about that in here, but that is how fast that line is going up here. And you can see the slope of this line is less than the slope of this line. So lower loading rate for the marathon runner. Peak vertical ground reaction force, peak braking force. So even this peak force is lower statistically. peak and vertical touchdown velocity of the rear foot. This is just how fast the foot's moving downwards at the moment of contact, then controls. So this was the between comparison of the marathon runner to all the control groups. Then they talk about the time. Contact time was longer, flight time was shorter, and duty factor greater in the marathoner. So the contact time is longer, and the flight time was shorter. Yep, the flight time was shorter, and therefore the duty factor was greater. So the time that the muscles were being active is actually increasing for a marathon runner. So that seems a little funny, but. And here's the joint power results. The knee were negative during the first stance. The marathoner had remarkably low values in peak power absorption. That's that negative power. And eccentric work, which is eccentric work, you just calculate as the area under the power versus time plot. Okay, and that's what we looked at here. So that blue line is lower, less negative, okay, less negative for the marathon runner. So the amount of energy absorbed, which we talk about for negative power, is less for the marathon runner. Lots of data here. We won't go through all that. And some neat data here. I'm not going to go too much into this, but what they're starting to do is show how the marathon runner is sort of quite unique compared to all these other runners. And that's sort of a neat thing. Okay, discussion section. Remember, I always talk about the discussion section. You'll find that most important observation right in that first paragraph. The extraordinary marathoner had lower running ground reaction forces when compared with a group of distance runners mapped by similar foot strike pattern during lower ground running of 3.3 meters per second. And then they go in and talk about the specifics of that observation. At the end of the day, what they're saying is the marathon runner is able to successfully complete the 100 marathons in 100 days because, this is graph's good to look at, he had lower peak forces, okay, a longer contact time, so he's applying a lower amount of force over a longer period of time, and less loading rate compared to the control groups. And so that is something that they talk about as possibly a factor explaining why he's able to run this type of ultra run event, which is really extreme. 100 marathons in 100 days. That's really quite extreme. All right, so interesting, but I was hoping for a lot more of data from the 100 days, but that's all right. You know, still got some really interesting stuff. At the end of the day, the purpose was to look at the unique biomechanical characteristics of this one runner compared to other runners of similar foot strike pattern. And at the end of the day, what they were able to conclude is that the marathon runner had lower forces, lower peak forces, lower eccentric power, and forces were applied over a longer period of time compared to the control group. And they suspect that this is what has allowed him to develop a running style, or he has developed this running style that allows him to be able to complete these ultra run events. All right, well, I hope you enjoyed that. I like it, and it's sort of fun to sort of dive into specific application to a single runner. I'm trying to understand why this runner is able to do what he is able to do. Okay, thank you.